I'm David Lapp, product manager for Spatial and Graph with Oracle. I'm joined by Jayant Sharma, director of product management for Spatial and Graph at Oracle. And we're going to be talking about the combination of autonomous database and Python for location-based analysis. And the context of location-based analysis really boils down to the premise really that everything happens somewhere, everything meaning all the information that we manage and the applications that we create and the services that we create and publish and use, everything relates somehow to things happening somewhere, incidents, events, activities. Now, between the Oracle database and in particular Oracle Autonomous Database with its ability to manage and process and perform queries on spatial data natively, combined with the incredible power of the whole world of machine learning and spatial data science libraries in Python, we have the opportunity to do some really cool stuff really quickly and easily by putting these things together. So the agenda today is really simple. In the next half an hour or so, I'm going to just quickly describe the spatial features in Autonomous Database, what the spatial sort of ecosystem looks like in Python, and then how to put those two things together to do useful things in the form of a couple of demonstrations. So for folks who may be more familiar with, generally familiar with the database, not necessarily with spatial, maybe there's folks that are Python centric here. The summary of spatial in Oracle database in general, it goes back decades and is very mature and very robust. And it's essentially amounts to the fact that we store all the forms of spatial data, both your basic points, lines, polygons, and combinations of those, as well as advanced types like connected networks, linear networks, geofencing, 3D data, geospatial imagery. We store really all forms of geospatial data natively with APIs to be able to process and manage that data natively in the database. And then up on top of that, you see that we have a set of apps, basically components that are deployed to provide useful functionality on top of that data, mapping, geocoding, et cetera, et cetera. So that's really what makes up the spatial features of Oracle database. And as I said, it's been around for a long, long time. That extends now to the Oracle Cloud, Oracle's Gen 2 Cloud, OCI. And that actually extends to every database in the Oracle Cloud. So from the customer managed and semi-customer managed databases in the Oracle Cloud, I should say Oracle semi-managed by you and Oracle. So whether you're deploying database onto a VM in Oracle Compute or using Oracle Database Cloud Services or Oracle Autonomous Databases, they all include spatial. So I'm focusing on autonomous today because that's what this demonstration is going to be built on. The features exist in all Oracle databases, all Oracle Cloud databases. There's a few details around autonomous that I call out here, which aren't per se about spatial limitations. They're just some aspects of autonomous databases that inherently limit your access to certain capabilities and access to certain pieces of the file system just because of the autonomous configuration. These slides are all shared with the rest of the slides from the developer live event. So all this will be available to you. The upshot, spatial is in every Oracle Cloud database. So that gives us our processing, spatial data management, spatial analysis, asking spatial questions. And then there's this whole ecosystem of spatial capabilities in Python. So that extends to spatial machine learning and spatial data science and all kinds of specialized analyses and all kinds of sort of industry-specific, domain-specific packages that are very widely adopted, very robust, and exist out there in that Python ecosystem. So it's to our great benefit to put these things together. Amongst those libraries, the three that I'll call special attention to, and the three that are the big part of the ecosystem that I'll show in the demo today, that are sort of on the tip of everyone's tongue with using Python and Spatial are, first of all, a library called Shapely, which is basically how you can create geometries in Python and do basic geometry handling, input, output different formats, and do basic geometry manipulations. Sort of the way that we handle geometries in the database with our native type. We have Shapely in Python. You have GeoPandas, which takes pandas, which is the data, sort of creating data structures and doing data operations, data frame operations in Python. And GeoPandas extends that to the geospatial realm. So instead of a data frame, you have a geodata frame, and all the sort of essential functionality around using what are sort of like spatial tables in Python. And then Spatial, which is a extremely powerful, very wide, very deep spatial data science library with all kinds of stuff that I'll barely scratch the surface of today, but it marries really nicely with the things that we do in the database. So the one other library I'll call attention to is the CX Oracle module, which is built and maintained by Oracle, it's open source, and it provides robust, with a capital R, robust access to Oracle database from Python. So not only being able to easily connect to the Oracle database and run queries and get results back, but it's aware of and has native sort of understanding of all kinds of advanced Oracle features so that they're really easy to use in Python. Dealing with types like an object type, like a geometry in the database becomes really easy with Python, with Python through CX Oracle, as does a lot of other advanced sorts of Oracle features that you don't need to code around. You just use this module and it has features to support them. And I have the GitHub link for folks to be able to see all kinds of examples and general getting started. So that's my quick preamble, because I really want to focus today on the demonstration. And I'm going to do a demonstration in a Jupyter notebook. And I've got a link here that perhaps Jayant, you could share in the chat, which is a link to just an exported HTML version of this whole notebook, or it's a PDF version of this whole notebook. So everything that I'm showing, you have access to. It has my contact information in it as well. So with that being said, let's now just jump in and see what all this looks like and how it works. So now I'm in a Jupyter notebook, and we're just going to start by acknowledging where the stuff I'm going to show comes from. It's a marrying together of autonomous database and Python with CX Oracle as the glue between them. In Python, it's really here going to be all about Spatial, the spatial data science library. And I have referenced the places where I've grabbed these really nice examples of Spatial-based spatial analysis notebooks, and I've adapted them and sort of morphed them into the use cases I'm showing, but they originated from here, and I want to make that an acknowledgement. So also my contact information, and then we'll begin. So for all of I'm going to show two scenarios. So for these two scenarios, the libraries that I need, we've just discussed, very straightforward. Of course, I need CX Oracle. We're going to connect to the database. Pandas for general data structures, GeoPandas for our geodata frames. I'm going to do some plotting, and then a whole bunch of Spatial items for the specific sort of models and algorithms that I want to run. I'm grabbing those Spatial items, and then I talked about Shapely as well. So Shapely knows how to load, how to incorporate data from all the most common formats of spatial data that's out there, including multiple formats that we in the database can publish natively. So it makes it very easy to connect together. And then NumPy for handling matrices and arrays. So any Python folks are going to be well familiar with all this stuff. So two scenarios, beginning with scenario one. In Oracle Autonomous Database, I have a warehouse full of US national auto crash data that it's meant for sort of data mining and machine learning. It has the time, it has the location, and it has all kinds of attributes and metrics that let you slice and dice that data. What we're going to do is use the database in Python to try to understand where are the areas that are particularly hot spots and particularly cold spots for where speeding is a major factor in what turn out to be fatal crashes. So that's our scenario. Where is speeding a major factor for fatal crashes? Data's all in Spatial. We have some models that we can run on data once we process it in Python. So we'll get started. First thing I'm going to do using this CX Oracle module is connect to Autonomous Database. I'm just storing credential information, and the cloud wallet exploded out into the file system. That's all. There's examples for all of that in the Oracle database and CX Oracle documentation. I mentioned CX Oracle is really smart with the Oracle database. We're going to be using geometries to bring geometries back from the database to Python. They're going to come back in a format that Python knows how to handle natively. And in particular, they're going to come back as these lobs that we're going to transform into. CX Oracle knows how to make it very efficient to do that by making one round trip instead of what would normally be multiple round trips for folks that are familiar with lob locators. So using CX Oracle, I'm going to tell it to make a single round trip, and then I'm just going to run a query. The query I'm going to run as follows. From a table, just as an example, from a table that stores a grid, and I'll explain why we're using a grid later, just we're going to summarize data within a grid. But I just want to bring geometries back as an example. So from this grid, I'm going to select the geometries in the database, and then I'm going to transform them using a native function we have in the database in Spatial to convert them to a format that Python can read natively. And that's WKT, well-known text. So just a basic SQL statement, and I'm going to return it, and I'm going to load it into a geodata frame in Python and look at the first few rows, and there we have it. So here's a bunch of geometries that have been retrieved from the Oracle Autonomous Database. We're looking at it in Python. Now that it's in Python, I can use Python libraries to view it, plot it, whatever. So I'll just do a basic plot of that result. So here we have it, just using the native plotting libraries. It turns out that GeoPandas, once you create a geodata frame, whether it was from Autonomous Database or anywhere, you can just plot it. And that's all I'm doing here. So what we're actually going to do is take all this huge volume of data that's being stored in the database with geometries for each traffic crash. And I want to use Spatial in the database to aggregate within each of these cells, what is the total percent of crashes that involve speeding in each of these cells. That's the metric that I'm going to calculate. So again, for every cell, aggregate all the crashes that fall within that cell, and then summarize the percent that involve speeding. So I can do that with another query here, and this is just a basic SQL statement that involves a spatial operation. This any interact is what's going to give me the result that is crashes, which are in this fatal accident reporting system table, and grids, and it's going to summarize and aggregate each crash within each grid, and then I've got a little formula here to get the percent of those crashes that involve speeding. So basic SQL, you could copy and paste it into SQL Developer and run it, but I'm going to take the result, get it into a geodata frame, and get the result. So here we have a result. Back from Oracle Autonomous Database, we have the identifier of each grid, a metric, which is the percent of crashes that involve speeding, and then the geometry, the shape of that little grid cell. So now that it's in Python, we can view the result. So here's just a sort of a qualitative view showing us the hot and cold areas in terms of where speeding was a major factor. What we're really interested though in is not just sort of painting a picture that's qualitative and you sort of squint and infer the hot spots and cold spots, even though there's some pretty clear sorts of patterns. We want to quantify and apply models, statistical models to this data so that we can be assured that the hot spots and cold spots we identify are truly statistically meaningful. So now that we've got the data into Python, Spatial has done the work behind the scenes, the data is in Python, we will use this PySal library to do the analysis. I've got the link for the homepage of PySal with all kinds of great examples, but I'm just going to focus on the following in this first example. We're going to need to perform for a hot spot, cold spot, sort of outlier type analysis. We're going to use models that rely on the fact that the data has a true spatial correlation. So we're not going to apply any models until we know that speeding, the factor of speeding involved with crashes is truly correlated with location, and affirm that and then move on. Now, how do we correlate some value like speed, whether speeding was involved or not? How do we correlate that with location? Well, if we were correlating two variables like home price and household income, you could imagine plotting those on two axes and seeing if there's a correlation, if they sort of form what looks like some type of relationship. But how do you correlate something like home prices with location? It's like correlate home prices with home prices. It doesn't intuitively make immediate sense, but it does when you think about what we want to do is we want to correlate something like home prices or the speeding factor of crashes, we want to correlate that value at one location with nearby locations, surrounding locations, and just does that correlate? Because if it does, then there's a correlation in space. Things are similar to nearby things. That's where this Spatial library kicks in, makes it easy to do all that kind of stuff. So the first thing we're going to do is use Spatial, and they've got all kinds of generic examples for this that I'm going to poke through quickly and just let you understand the meaning behind it, not all the details in the in the syntax. But we're able to take that data and create a metric from that entire geodata frame of all the data, create a metric that defines the sort of the degree of spatial autocorrelation as a whole. We've got this number, 0.352, et cetera, which is a measure of how correlated in space is the role of speeding with crashes. Now, this number in itself doesn't tell us much, but what does tell us a lot is if we compare that to if the data were spatially random. So we do, again, using Spatial, it'll automatically run a whole series of randomized simulations and take that metric that we're evaluating and just, if it was completely random, what type of values would we expect? And the values that we would expect if it's random are the values under the blue bell curve, right? And so, and it's sort of a standard deviation on either side. And our value is in red. This tells us that the correlation of speeding affecting crashes is very statistically significantly correlated with location. Values are very similar to nearby values as a whole. This gives us the sort of the green light to say, okay, now we can move on with looking for hot spots and cold spots because they do have meaning. So to do that, we move from this global view of correlation in space to local. And what that means is that once again, Spatial lets us calculate a sort of build this object, which is referred to as local spatial autocorrelation. LISA is an acronym, local indication of spatial autocorrelation. So we calculate that thing, and then it has a bunch of properties that tell us interesting things. First of all, for every grid cell, it tells us what is the probability that the value in that grid cell is spatially random or not versus being correlated with nearby values. So this guy here would be 4%. There's a 4% chance. Here it's a 10% chance. So this is telling us that whatever else we see, how likely is it that what we're seeing there is spatially random or not, right? So we want to we're going to want to use locations and trust locations where the probability of being random is very, very low. The next thing that this object tells us is for each item, for each grid cell, which of 4 quadrants does that cell reside in? And the 4 quadrants are as follows. Quadrant 1 means that that cell has a high value surrounded by other high values. That's a hotspot. Quadrant 2 means that that cell has a low value surrounded by high values. Quadrant 3 means that it's a low value surrounded by other low values. That's a cold spot, and so forth. So here we see the quadrants that each cell lives in. We can see this cell is hotspot, 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 cold spot, outlier, et cetera, et cetera. Now that we have that, we simply want to say, I want to see all the grid cells where the probability of being random is less than 5%, and it's a hotspot, meaning quadrant equals 1. So I'll run that, and here's our hotspots. These are the statistically significant areas where speeding is unusually high factor in causing fatal accidents. And similarly, we'll do the same thing with cold spots. These are the areas where speeding is typically, a concentration of areas where it's not, where fatal crashes are not due to speeding. You could squint and look at the qualitative sort of heat maps of the raw data, just sort of classified with color, but this is something very different. This is quantified and defensible, and a very straightforward example of things that can get much, much deeper. And of course, the purpose of this is just as a launching pad for maybe combining other attributes and dimensions and combining this with other machine learning models and other factors to see what's really at play, what's root cause, what are mitigating sorts of actions, how well have different programs in different areas been effective. If we had been doing programs in these areas to reduce speeding, and we see this kind of result after time, this is a really quantitative, meaningful result. So that's example one. Example one from the standpoint of a pure spatial analysis. Only looking at space and looking at the correlation of some metric with space, hot spots, cold spots, we could go on to outliers, etc. The next scenario will take this one step further and add time. So while that was a spatial analysis, we're now going to look at a spatiotemporal analysis. Once again, the database is great at managing the huge volumes of data behind this spatial temporal data. The database can manage, pre-process that data in all kinds of ways, spatially, all kinds of spatial aggregations, and then get that data set up so that we can get into some spatiotemporal modeling and deeper specialized analysis in Python. So that's exactly what we're going to do here now. The scenario is as follows. So now our data is unemployment data, moving from car crash data to unemployment data, but it's historical unemployment data for the country by county. And what we're going to do is the following. We've got all this historical detailed data by these little counties. I want to, in this scenario, say that there's a particular region of interest that I'll define in a moment, and it's only within that custom region that I want to perform this analysis. And I'll say that it's within that region that some type of workforce enablement program and other unemployment mitigating actions have been taken in some multi-state consortium, say. And we want to look in detail at how the spatial temporal sort of evolution of unemployment can be measured. So that's what we're going to do in this case. So once again, to start with, I'm just going to use the CX Oracle module to connect again to Oracle database. Do the same thing. We're going to tell Python for long objects like these big geometries, if I have them, make one round trip instead of two. Thank you, CX Oracle. Make that simple. And now we can begin. So first of all, the raw data at play here. Just going to grab the first 10 rows of a Bureau of Labor Statistics unemployment table, multi-year table, and it's normalized data, sort of off the shelf. So I've got state and county codes, the year, and the unemployment percent. That's my raw sort of business data. The other thing I want to do is only have this particular region of interest be where we do our analysis. So here I have a region that I'm going to say surrounds these set of states. I want to create one sort of melt together those 6 states, and that's what a spatial operation, aggregate union does. I'm going to aggregate them, and then I'm going to put a buffer around them, a little extra area around them. Say I had a consortium of workforce enablement, and it was these states, and it included some surrounding areas. So I'm using spatial to define this area of interest, and then we'll take a look at that. So I'm going to look at it in a slightly different way this time. This time, I'm just creating a geodata frame with that geometry, and I'm just printing out what that geometry looks like. It also turns out that Shapely, that tool I told you about, if I just say, list a geometry, Shapely geometry, it'll create a little cartoon picture of it, just as an aside. That's fine, but it's floating in space. That doesn't really help us much, but it's easy to see that, yeah, we created some funny shape by combining these geometries, putting a buffer around it, all in autonomous database, display it in Python. Now we'll look at it in context. So let's view the region on a map in Python. So here's what it looks like. Again, this is the same shape we're looking at here, but just using Python to lay it on top of the states. So you can see that in autonomous database, we did a spatial aggregation, put a buffer around it. It's within this area that we want to conduct our spatiotemporal analysis of unemployment. Okay, so now having done that, we saw that we have data that's in a normalized format, just county year unemployment, Now we have our area that we know how to create using a spatial query. Now we need to get the data sort of munged and prepared, like the data engineering needed to feed the model that we're going to run, because that model needs information prepared in a certain format. So the typical sort of data engineering step. Because we're just connected to Autonomous Database and we've got all the features we need in the database, I don't have to get all the raw data in here and do the data engineering in Python and pandas and a ton of that work. I can just get it most of the way there with a single query. You know, so for the SQL folks, like using the with clause, which is absolutely tremendous, powerful feature, I can sort of get everything prepared that I need. So the first thing I'm going to do is with the with clause, create sort of a virtual table here that pivots my data, because I need the data to be fed in as time series, pivoted, not as a normalized form. So I'm going to create pivoted data. And then I'm also going to create a little virtual step, which is that exact same spatial aggregate buffer thing. And then I'm going to run, using those two, a spatial query, which is going to do the spatial relationship of the counties to only get the ones that are within that area of interest that I have. I'm also going to grab the state, join to the lookup table to get the state names. And then I'm going to bring back not just the geometry of the counties, but I'm going to bring back this spatial function that provides it in the format that Python can read readily. So with this one query, I'll run that, and now I've got a cursor that I can look at some data from. So here is the result of taking that raw data that we saw a moment ago, pivot it, grab the geometry, bring in the state and county. Now I've got the data in the format I need. Now, just like we did something qualitative before, we could do something qualitative again. Just sort of classify the data over time and look at it in a map. And I know I've got like 2 or 3 minutes left, and that's all I need before we go to Q&A. So, so this ought to render momentarily. I guess it's sort of pulling a lot of data now into Python for that plot. So while I wait for that, I will describe what we're going to do next. So in order to do a quantitative analysis of this data, we're going to use not just a spatial correlation like we did before, but something called a discrete Markov chain. And what that allows us to do is look at data over time where the data has values that can take on some certain number of states. And there's our, sorry about the delay, but there's our qualitative data over time. Every other year I'm plotting. All right, but what we want to do is say that to classify the data in some way, we're going to classify it into quintiles, 5 bins, and then look at the probability of unemployment changing over time. And the classic example is if we measured weather and said it can only be sunny or rainy. We did lots and lots of measurements over lots and lots of time periods, and then you come up with a result that says if it's a rainy day today, there's an 80% chance that tomorrow will be rainy, 20% chance, 80% chance tomorrow will be sunny, 20% chance rainy. And similarly, if it's rainy, there's only a 70% chance that it'll change to sunny. That's the classic Markov sort of example. And we're going to do something like that with the unemployment data. To do it, we need to feed a bunch of time series into this model. And the time series that we need to feed are for each county, a time series of unemployment over time, but not just the raw unemployment data, classified into some discrete number of bins. So what we're going to input is a time series for each county where we've got a value for each year, and the value is going to be the quintile, where we divide all the data up into 5 even bins. And so this would say that for this county, it started in the 2nd quintile, then it dropped to the 3rd, eventually went up to the 1st, and the unemployment's moving up and down, and that's what we're going to feed the model. So a little bit more sort of pivoting and data engineering in here to create those bins. And I eventually just pivot the data so that I've got 1,271 counties. I have 1,271 arrays, and each one of those arrays is a time series over 14 years. So here's the time series for county 1, time series for county 2, with the quintiles of unemployment for each of those counties over time. So I now, just like we did in the first example, it lets me create sort of an object with all the results I need in it. And I'm going to, because of time, jump over a few things here. They're all in the notebook because I know we need to move along. But the one thing that I will show is I need to make sure that the data are not spatially random before I start to look at the real spatial results. So I'm going to run something right here, which appears to be, it must be a little bandwidth issue here. Okay. So this is not rendering for me. And there it is. Okay, so this is showing me my spatial correlation over time up in blue, and the possible sort of random scenarios are down here between green and orange. I am not random. I am spatially correlated over time. Now all I have to do is look at the results of this spatial Markov result, the spatial temporal result. It just gives it to us automatically, a summary in this format, which is tabular, sort of hard to interpret. So I'm going to visualize it in a color-coded form, and this will be where we can make our conclusions. So to explain what this gives us, for every county in my area of interest, the results are broken up into each of these charts that are titled spatial lag 1, 2, 3, 4, 5. What these labels mean are what is the surrounding unemployment compared to my unemployment. So if my county is in spatial lag 1, means I'm surrounded by the lowest unemployment. If for my county I'm in spatial lag 5, that means I'm surrounded by the highest unemployment. Each of these charts really means what is the regional context, the regional setting of unemployment. And then it's within these charts that shows us what are the probabilities that my county's unemployment will change in any given way, again, based on the surrounding unemployment. So let's start with spatial lag 5. That means surrounding unemployment is at the highest quintile, the highest tier. I'm surrounded by high unemployment. The rows in this chart refer to my initial state of unemployment in my county. The columns refer to what the unemployment is predicted to be in the next state. So if surrounding unemployment is at the highest level, if my unemployment starts in some time period at the highest level, there is a 60% chance that it will stay at the highest level. What if my surrounding unemployment is one step down? If the surrounding unemployment for that same county is only in the 4th quintile, in other words, same county, everything's the same except the surrounding unemployment is just a little lower, then if I've got that same top level of initial unemployment, the probability of remaining at that highest level of unemployment drops to 50%. So the probability that the highest unemployment will remain the highest unemployment is reduced by 10% if surrounding unemployment is reduced by one level. And you can go on and on looking at the different scenarios of where you start, where you end, and what surrounds you to get those kinds of space-time inferences. Again, it's all about how something, in this case like unemployment, will change over space based on regional setting, regional context. This is all one of multiple types of spatiotemporal analysis that this Python module provides. This is only one, there's others, and they're each suitable for certain scenarios and not for others. For this particular scenario, binning unemployment over time, looking at it regionally, this is a reasonable approach. But again, there's others. And the notebook here, as I said, is all available to you, at this link that we're gonna share. So just to wrap up what you've seen, we did all the spatial data management, processing, basic analysis, spatial relationship analysis in the database, the spatial ML, deep learning, well, it didn't show deep learning, but the spatial algorithms and data science was in Python, and they work really, really well together. Now, the next thing that we're gonna do is to take a pause, and we are gonna switch to Q&A, and Jayant Sharma, who I mentioned, is on the line. We also have on the line other experts, Shiva Ravada, who leads all of spatial development at Oracle, and Anthony Tininga, who is a Python, Python and developer expert, and who's actually the author of the CX Oracle module. So Jayant, maybe I'll turn it over to you if there's any questions in the chat.
Sure. But while we're looking at that, there was some earlier, most of them have been addressed, but there was one repeated pattern, which was, how do I try this out myself? I mean, people were happy with the static version, but they want the live version too that they can go through. So do you want to comment on that?
Yeah, so the static version is what you can grab right now. We will have examples of this that we are putting together for sort of a whole cookbook, start to finish, sort of a self-guided tutorial. And Oracle there's several vehicles that Oracle has for providing that kind of stuff, but there's a really terrific new one, Oracle Live Labs. And lots of great content is rapidly going up on that Live Labs environment. And that is what we're going to do with this.
So this had a lot of data science and machine learning in it. And we've also heard about the data science cloud. So can these two things be used together?
Yeah, absolutely. So the data science cloud makes it easy to work with stuff in the Oracle database. The Oracle Data Science Cloud has some spatial libraries. GeoPandas, is there. Others are going to be introduced, so it's doable now, but it's even going to be more and more sort of cohesive. And what basically the plan is that what the stuff that you saw me doing that I sort of put together myself, you'll be able to do the exact same sort of flow in the Oracle Data Science environment.
All right, thank you. Maybe another one or two. Let me just check. So you talked about the GeoPandas and the data science thing. Will there be something like a Python library for using directly with the database that does all the spatial features along with
there will, and it's something that we're working on. Maybe I'll turn it over to Shiva for a moment to be the sort of the final word on that answer.
So today, if you want to do any of this type of stuff, you have to assemble a lot of the third-party libraries and then kind of build a system that works for doing data science with the spatial. So what we are building for a future release is to bring all of these things together into Oracle platform. So that way, from a developer point of view, you will have a single source to get all of these things. It will be like it will be an Oracle platform. So that way, you don't have to worry about assembling all of these third-party libraries. And then in this platform, we will provide all of the tools that we would need to build a workflow like this, and even more complex spatial and AI model building blocks will be part of that whole platform that we are building.
Perfect, thanks.
Okay, there was another question from the audience. Has there been any experience of applying this to electric utilities? So David, you just work with the O-Power folks. You may want to answer that.
Yeah, absolutely. As Jayant just mentioned, we're working with a variety of utilities teams, and O-Power, which was an Oracle acquisition, is one of the teams in particular that has a very strong sort of whole data science focus. And so this is very, very much, so a specific example in utilities has to do with energy savings and where different programs for energy savings are having more or less of an impact, and how that relates to lots of different factors at play. And so one of those factors is location and location relationships. And so that's sort of outcomes that have to do with looking at energy efficiency and energy, the reduction in consumption, and having spatial models be part of evaluating that effectiveness is something that we're actually already helping our utility teams working on. Jayant, if there's anything else you want to add, that's fine. That's one that we're doing right now.
That covered it. That the other thing to point over there was a lot of it did in fact use the types of libraries you just mentioned. So besides understanding efficiency, they also wanted to understand consumption patterns, and that was doing the spatiotemporal analysis in using similar modeling techniques. So two other questions. One was which was the notebook that you used in this? Was it Jupyter, or was it something from ADV? What was the notebook?
Yeah, that was just a plain vanilla Jupyter notebook. I'm running Anaconda, container, and so that wasn't part of any kind of hosted service. It was just vanilla Jupyter.
Okay, so one last question, since you have to wrap up in another minute, was have you noticed any performance problems when injecting raw data processed from the server into a view such as a Django website? I'll just take a initial stab at that, and then you and Shiva can add. So we've done a lot of this with Apex, which is a rapid application development framework, which actually lets you very quickly create websites based on your data in an Oracle database. And we have not seen performance issues in Apex being updated. I'm not personally familiar with Django, but David, if you sure want to add.
Yeah, I don't have anything to add to that. Sorry.
I don't have any experience with that one.
All right,
one thing, Jayant, that I wanted to do was put in the chat the Live Labs link to everyone, if I'm able to. So whoops, and of course I did a typo with the word live in Live Labs, but this is the environment where you'll already see lots of great self-guided workshops and tutorials, and this is where you'll see more and more of this stuff from us. So I'm going to, Jayant, I think that's about time. So, and I actually have right here, if I can get rid of the chat window, I've got Live Labs open here just so folks can see it. But I did want to get rid of this, and sorry here, as I call attention finally to the fact that there are a couple of great sessions coming right up on our heels here, both a graph session by Melly and an Apex session by Joel. So between those two sessions, hopefully there's something for everyone here. So please stick around and join one of those two excellent sessions. And I really thank everyone for your attendance, and hope this was helpful, and look forward to hopefully connecting with some of you. Take care and thanks.